A previous video looked at a simple loop antenna and visualized part of the AM broadcast band using an FFT on an oscilloscope. This got me thinking a bit more about measuring RF spectra using common bench tools. In this video, we'll look a little more closely at the medium frequency and high frequency spectrum, using receivers and an oscilloscope as a crude approximation to a spectrum analyzer. Let's get started. First off, I wanted to look at the open loop again, with no capacity added. Just more loops of wire relative to the previous video. The reason I did that was I wanted to increase the terminal voltage a bit, just to get less noisy readings. So before I think I had 6 loops of wire on the loop antenna, and now I've got 12. Unfortunately, the Rigol doesn't have an averaging feature for the FFT trace, so there's going to be lots of fluctuations in the video, as you can see already. But that said, you can see several broadcast band stations in this spectrum. So just want to zoom in a little bit here and point those out. So first of all, you can see that we are on 500 kilohertz per division. The broadcast band starts here. So this is 0 frequency, this is 500 kilohertz, this is 1 megahertz, this is 1.5 megahertz, and this spike right here is a station at 1600 kilohertz, or 1.6 megahertz. Just underneath that you see a couple of stations, one that turns out to be at 1500 kilohertz, and the other turns out to be 1540. And you can see those bouncing up and down. The 1600 kilohertz station is very strong. The 1540 station is up and down a bit, and it's weaker than 1600. And then you have 1500, which is right here on that graticule, again bouncing up and down. Well, as you go down in frequency, you see other persistent stations, other persistent spikes that are less up and down than others, until you get down to the lower part of the broadcast band. And down here at the bottom you see, again, 2 or 3 stations that are bunched up. One of those is at 570 kilohertz, one of them is at 630 kilohertz, and another one is at 780 kilohertz. Just one other fairly prominent feature in this spectrum is a spike here that's fairly persistent, and that's at 980 kilohertz. Now I want to change the time sweep on this and go up a bit, so now the graticules represent steps of 1 megahertz, and I'm actually going to go up a bit more so that each one of these graticules represents 2.5 megahertz. So there's 2.5, 5 megahertz, 10 megahertz. And well, you can't see it right now, but let's just wait a little bit. It's probably because the atmospheric conditions have changed. But watch here, just below the 10 megahertz line. Just before I started filming, there was a very prominent spike, and just under 10 megahertz. And so I thought, no, that can't possibly be a station on shortwave, because it was just so strong. And then so what I did was I tuned it in and found that at 9820 kilohertz, I think that was the frequency, in fact there was an extraordinarily strong, over 20 over S9 station booming in here at this location. So it was really quite striking. I'm not seeing it come back now. Maybe they went off the air. And in fact, when I turned the receiver on, it was 9840 kilohertz. Basically all you hear is noise. So we'll come back a little bit later in the video and see if that station reappears. So let's get back down to our broadcast band. And what I want to do now is add a capacitive element to the circuit and show that these stations can be picked out preferentially through the broadcast band on a loop antenna. So instead of making my own loop antenna, I went ahead and ordered this loop antenna. This is branded Texsun. There are several essentially clones of this, or maybe this is a clone of something else, but there are several of these sort of antennas on the market. They're not terribly expensive, and they look better than anything that I could gin up on my bench, so that's why I got this. This is just several loops of copper wire, and in parallel with a capacitor that one changes here, and this is designed so that the resonant frequency goes from around 500 kilohertz to around 1700 kilohertz. It spans the broadcast band. So what I want to do is now move in for a much closer shot and show how the spectrum changes when I go from the non-resonant loop to the resonant loop, and then show how the Q of this antenna is such that it can separate out stations that are quite closely packed. Alright, here's the spectrum again, and this is with the 12 loops of wire without any capacitor in the circuit. And what I'm going to do is now take this off and put it on to the resonant loop. I want you to watch how the spectrum changes. So we've got these very prominent spikes that persist, and these correspond to different stations in the broadcast band. So I'm going to take that away. And now I've got the loop hooked up. First thing that you notice is that the spectrum looks like it's mostly noise, that the persistent patterns go away. Again, just noisy spectrum, fairly flat, with a spike down here at 0 frequency like you would expect. Okay, now I'm going to start tuning from the bottom of the band, and we should see, I want you to watch right around in here, you should see AM 570 spike up. And there you go. So right there is that first station down at the bottom of the band. Right, there we go. We can move through it and back down to it. Okay, this transmitter is fairly close to my home location, and so you can see that it carries a lot of energy into the loop. By the way, you can essentially make this signal go away if I rotate my loop 90 degrees. I'm rotating it right now. Notice how the spike gets much less prominent and in fact fades into the noise. It's still there, just because I haven't quite nulled it out, but that's pretty good, and that's 90 degrees. The loop orientation is 90 degrees relative to what I had it before. So I'm going to now move it back, and there you see the station returns. And this is one of the great powers of the loop antenna, is the directionality. Alright, I'm going to keep moving up band here. And there is another station in this market. Let's see what frequency that is. So these are 500 kilohertz divisions. So this is 500 kilohertz, 600, 700. So it's just less than 800. And this is AM 780, a station, again, in this market that's not terribly far away. So let's keep moving up band. There you see you could really get it to resonate there. So let's move up band a little bit more. So I'm just increasing the variable capacitor there. And there we go. So we get this spike here, and this is AM 980, a station, again, fairly close. And you can see that there's another station, another spike right here that is beginning to pop up. So if I adjust this just a tad, I can get that, okay? And if I keep moving up, there's another station. So one of those was 980. This is probably 1030. And if I go just a little bit more, okay. And so now, right, there's another station that pops up there. And this is just a selective tuner, essentially. All right. There's no question as to what frequency this is. 500 kilohertz, 1 megahertz, 1.5 megahertz. This is 1500 AM. And if you look very, very closely, you can see there's just another pip, another little spike just to the right of that. And see if we can get that in a little bit better. There we go. That's AM 1540. So I'm going to move back down again, pick up AM 1500, move up a bit, and you can see 1540 emerge. It's not nearly as powerful as 1500. And then go up a little bit more, and there is AM 1600. There it is, a little bit better. There it is. Really tuned it in there. And backing off just a little bit, you can see the time series trace here. As I sweep through the resonance, you can see that the time series really increases and then decreases. And at maximum amplitude in the time domain, up here, the yellow trace, you get maximum amplitude in the frequency trace. That scales with energy carried by the wave. So let's move on just a bit, and let's go back and see if propagation conditions have improved to the point where I can show you that 10 megahertz signal. Okay, I've changed the time sweep on this so that now each division is 2.5 megahertz. Let me zoom in on this a bit. Okay. So 2.5, 5, 7.5, 10. And if you look right there, just less than 10, there you can see it, it's emerging from the noise. You see this pip, this spike, that changes. As I said, before I started filming, shooting this video, this was very prominent. So what I did was I tuned my receiver into this and went to just shy of 10 megahertz. And let's zoom out a bit here. And you can see now as I've got noise, 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 9.6, 9.7, 9.8, 9.84. It's a very strong signal. And in fact, if I attenuate, if I add 10 dB of attenuation into it, I still have a very strong signal. It's still 20 over 10. And if I put 20 dB of attenuation in, I've still got a 20 over signal. So this is a very strong domestic religious broadcaster at 980. I'm sorry, at 9.84 megahertz. And let's kill the audio because it's going to drive me crazy. And again, let's zoom in here. And again, you can see that spike, 510 megahertz, right there. Okay. even at 20 over, there we go. Even at 20 over, it's, you know, kind of dancing around in the noise. And unfortunately, the Rigol oscilloscope, at least as far as I've been able to determine, cannot average FFT signals. If it did, we could average out a lot of this noise and get the persistent spectral features that correspond to the different stations. Not a spectrum analyzer, but it approximates one by taking the Fourier transform of the time series voltage measurement and transforming that into frequency space. All right, and then finally, just to wrap up this this video on loops, here is the loop antenna sitting next to a Grundig satellite 750 receiver, and I've tuned in the frequency 1010 kilohertz, so 1.01 megahertz. There is a station near here, not near here, about 50 miles away, that broadcasts during the daytime at a power of 250 watts. This is a very, very local coverage radio station, and it's difficult to pick up at this location, especially given that my shop is actually in the basement. So what I'm going to do here is I've got the loop set next to the antenna. Remember, this is an antenna that is adjustable, that, you know, it spins around and it gets dirty, and it's a stupid design. But anyway, I've got the loop so that it is perpendicular to the axis of that rotatable antenna. And I'm going to turn the volume up here. So I think possibly you can hear, turn it up a little bit more, that there is just basically noise. And I'm going to zoom in a bit here so that you can see the S meter. Zoom in just a little bit more. Alright, well, yeah, I'll put the S meter in the middle of the shot here. Okay, and now I'm just going to start, I'm going to put the attenuation, antenna attenuation, at 20 dB. Right, so the audio essentially went away. And I'm going to start tuning this loop. Listen here. Right there, we've hit a resonance. The S meter barely moves. But now let me take some of the attenuation off. So I took off 10 dB. I've now got a total of 20 dB attenuation. Let me detune the loop. So that's what the signal sounds like without the loop on resonance. And let's go back on resonance. So you see we've got a dramatic amount of energy being dumped in here to the antenna from the loop. And now that's with all the attenuation taken off. I'll get the volume down a little bit. But notice how with the loop tuned, I've got S meter readings. There we go. Of, you know, maybe, what, S4, S5, it's kind of hard to see. I'll detune the loop. So this is what it would sound like barefoot, if you will, with no loop near the receiver, just with the receiver's antenna alone. And as I tune the loop up to resonance, okay, so you can see there's a signal there. Now, a 250 watt station 50 miles away in the basement is probably not going to be audible even with this loop. But you can see I've now got over an S9 signal. At night, there are so many signals coming in from all over that using a loop like this can be a bit of a challenge because the signals are generally strong to begin with, and so the loop really, you know, only helps you when there's just a whisper of a station on frequency. Then you can bring the loop nearby the receiver and tune it up. And at nighttime, when the atmospheric noise and some of the man-made noise is not present, the effects can be quite dramatic. We'll probably move on from loop antennas in the next video. I have a new receiver that I'll probably do a quick review of, a travel portable radio that impresses me a lot, so we'll probably get to that very shortly. Hope you found this interesting. If so, please give it a big thumbs up below, and as always, thanks for watching.